I'm Simon Clegg. This talk is an examination of assumptions underlying the definition of total pH and the implications for measured carbonate dissociation constants in seawater. In our project, we are developing chemical speciation models of tris buffers used to calibrate the seawater total pH scale, and also models of seawater including carbonate equilibria. In this talk, we will provide an overview of some of our recent findings. Now, looking at the lower half of the slide, in the sequence observations and laboratory measurements through models to applications, we focus on lab measurements and models in our project. In this presentation, we first distinguish the operationally defined total pH, item A, from B, the conventional thermodynamic total pH, which was obtained by quantifying for the first time the assumptions inherent in the operational value. We will also explain the meaning of total pH extrapolated to zero buffer molality and some limitations in our current knowledge. Now, the reason for the difference between A and B above is that the buffer pH is calculated from two quantities, E star and E, both of them EMFs, from two solutions, 1 and 2 here, that differ slightly in composition, one with buffer and one without. Second, there are the carbonate constants K1 and K2 in seawater, expressions given here, which we would like to know and to be able to calculate at different salinities and temperatures. Now consider that we have a pH A defined and calibrated in the lab, B measured at C, and C determined as an element of laboratory measurements determining the values of K1 and K2. So our questions are, to what extent are A, B and C pH measurements actually consistent? Now, this is not an easy question to answer and is not something we have had time to investigate in detail. However, we can ask a simpler question, which is, to what extent does this consistency matter? Laboratory measured K1 and K2 are really rather scattered, as we'll show. So below a certain level, pH consistency probably isn't going to be important. So, pH on the total scale. So let's first distinguish operational total pH that oceanographers use from the thermodynamic total pH. Now this plot shows the operational pH for various buffer molalities, the x-axis, in salinity 35 seawater at 25 degrees, measured by Delvals and Dixon. This is their figure 1. You can see that the pH declines somewhat as buffer molality is reduced. And now moving on, and here is the modelled operational total pH in blue, corresponding to the previous slide. As the buffer concentration tends towards zero, the pH heads down towards neutral, as one would expect. Point A here identifies the solution containing the 0.04 mole per kilogram of buffer, and point C will be explained shortly. This here is the magnitude of the typical uncertainty in an EMF measurement from which pH is determined. And here we've added the thermodynamic total pH in the buffer, in red here, determined by estimating, using our model, the assumptions inherent in the operational definition. Now points A and B on the two scales, or versions of the scale, are for the same buffer molality. And the difference between the operational here and thermodynamic here total pH is about 0.004 pH units at 25 centigrade. Now the uncertainty in that figure is currently about 30 to 50%, but we are working to improve it. And what is point C? Well, in a hand-waving sort of way, it's the buffer pH where the influence of the buffer on the artificial seawater medium has been removed. Now, more exactly, it's the pH that either of the two measures would have if all seawater components, or artificial seawater components, had the same activity coefficients as in pure artificial seawater, and those of the buffer substance were the same as if they had only a trace presence in the artificial seawater. At point C, the values, the pHs, of the two measures, operational pH and thermodynamic pH, are necessarily the same. Next, calibration of the total pH scale, ranges of salinity and temperature. So this is a little bit of an aside. The range over which total pH scale at the present time is calibrated. Now on this plot, temperature here, salinity on the x-axis. So the work of Delvals and Dixon, essentially 20 to 40 salinity. Papadimitriou at high salinities and low temperatures. And Muller et al. From 5 to about 20 salinity. So we have found in the course of our work that the results of Muller et al. Are inconsistent with those of Delvals and Dixon at about the 0.01 pH level. And the reason for this turns out to be very simple, and that's the formula used by Muller et al. For calculating experimental solution compositions does not yield the results intended, which is that they should extrapolate to artificial seawater composition for zero added buffer or zero added HCl in their experiments to determine standard EMFs. And the consequence of this is that their equations for total pH are systematically different from what they should be, and really because of that the total pH scale kind of remains uncalibrated below salinities of 20, which seems to us a gap that somebody ought to fill. Now I'm not going to go into any further details of this here, but I'd be happy to provide more information to anybody interested. So, comparisons of K1, K2 and their product. Now this table, which I am not going to go through in detail, lists some of the key studies determining K1, K2 or their product, and on the right here, how pH was calibrated in these experiments. Now, how the experimental pH relates to the operational total and the thermodynamic total is not straightforward, although we can say in general that those studies using spectrophotometry to determine pH would be most likely to be subject to the inconsistency that we've identified between operational and thermodynamic pH. So we took a very simple approach to looking at this. So what we did was to compare the scatter in the data for these K1 and K2 constants with the magnitude of possible pH inconsistencies, simply to see whether their effects, the pH effects that is, on the measured K1 and K2 might be significant or not. And these comparisons, or at least plots of the scatter of K1 and K2, are not well made in the literature, I think, by which I simply mean that the graphs in various publications don't show all that I think they could. Now, our simple measure of pH inconsistencies, denoted delta pH on the following slides, is 0.004 pH units, the difference between the operationally defined and thermodynamic pH that we showed earlier. Now, how do we make these comparisons? We plot the difference between model calculated and measured K1 and K2 as a function of salinity just at 25 degrees for the purpose of these comparisons. And here we're chiefly interested really in how the data compare with each other and not with the model, although the comparisons with the model do show up some interesting things. And you can see that delta pH here is rather small compared to the scatter in this particular data set. And next, we have added on the results of Luca et al. From Meerbach's titrations. And we see here that there's generally rather good agreement with Millero's EMF measurements, but also a large scatter relative to the magnitude of delta pH here. Next, in green, we add the EMF results of Motica Prieto et al., perhaps a little higher than Luca's experiments, that is to say, smaller deviations relative to the model. But we see that this data set has a similar level of scatter to the others and pretty good agreement overall. Now finally, we have added as the open symbols, circles and triangles here, the results and the fitting equations of Goyer and Poisson and of Roy et al. And they're both rather more scattered and I would say discordant with the other data. And our overall conclusion is simply that the scatter in the data, even for those data sets that would generally be considered reliable in quotes, is larger than the possible pH inconsistency, delta pH, down here. Next, we carry out exactly the same kind of comparison with K2 for different salinities at 25 degrees centigrade. Again, we begin in blue here with the 2006 results of Millero et al. And the fitting equation in blue here, first of all, it does not fit the data at moderate to high salinities, ideally one would say, but also it can be shown that in this region here, that it is unphysical and unrealistic. And at the bottom, I've indicated the magnitude of delta pH again, and it's small in comparison to the scatter in the data set, rather as it was in the case for K1. Again, our second step is to add the results of Luca et al., the red squares here, and we see that over the common salinity range, they agree well with those of Millero. And again, the story about the scatter in the data is much as it has been on the previous slides. But as was the case for K1, the results of Goyer and Poisson and Roy et al. Are rather different from those of the other studies. So our overall conclusion is that the work of Millero et al. And Luca are consistent, the studies are consistent with one another, although the equation of Millero and his 2010 equation, I think, behaves rather similarly to this, does not represent the data especially well and is not realistic at salinities below 10 or so. The conclusion with regard to pH consistency is, again, as it was for K1, the magnitude of delta pH here is very small and less than the scatter in these data sets here. Finally, the same kind of plot, but for the product K1 times K2. Here we see the values of Milero et al. 2006, again constructed from their individual determinations of K1 and K2. And we see that the pattern of residuals is essentially the same as it was for measurements of K2. And here is their fitting equation, which also shows the same behavior as I have commented on before. And at the bottom here, we've got our measure of possible pH inconsistency. And again, it's quite small compared to the scatter in those data. Next, in green, we add the results of Prieto et al., which are also EMF studies. There's quite good agreement with the work of Milero et al., but only above salinity of 15 or so. And for some of these experiments by Prieto et al., the pH was determined spectrophotometrically, but I don't believe that there's a notable difference between those results and those which were in which the pH was not determined in that way. Last, in magenta, we add the recent results of Schockman and Byrne, determined by a quite different method, additions of bicarbonate until a invariant pH is obtained, and that pH is determined by spectrophotometry. And we can see, looking on the plot here, there is rather good agreement with the work of Milero and of Prieto et al. Over the common salinity range. And rather like K2, the product of the two equilibrium constants is very poorly determined below about salinity 15. And I would suggest that in future, with an improved model, that it may be model calculated, model estimated values in this low salinity range that are the best way of determining them, but that's really another story. Finally, to summarize, we have estimated for the first time the conventional thermodynamic pH of the Tris buffers used to calibrate the total pH scale. For 0.04 mole per kilogram buffer, salinity 35 and 25 degrees centigrade, it is about 0.0044 pH units lower than the operationally defined value of Delvalle and Dixon, although there does remain a significant uncertainty in that number. So we have explained the meaning of the linearly extrapolated buffer pH for a medium composition of pure artificial seawater. And next we have examined measurements of the carbonate K1 and K2 constants, and we've compared our chemical speciation model to some of the available data and also the fitting equations produced by the authors of those studies, and found the following. First, the scatter in K1, K2 and their product is greater than the differences between the pH types according to our very simple measure, delta pH. We note that the equations of Milero 2006 for K2 and K1 times K2 don't represent the data as well as they might, and they are also not physically realistic for salinities below about 10. The data for low salinities are rather few, and they're also very scattered, which explains partly the above observation. And we believe that an improved model would be better able to provide the values of the constants at very low salinities, but that's really another subject. So thank you for your attention, and I'll be happy to answer questions during the session. And I will leave you with these credits and references, and we're also very grateful to our funders, NSF in the United States, NERC in the UK, and also to SCORE. Thank you again for your attention.